And today I'm going to be talking about developing predictive models of turbulent heating in space and astrophysical plasmas. Of course, as a scientist, I didn't do any of this alone. I've got many collaborators, many more than this, but these are the ones that have worked primarily on the work associated here. The ones in red are the people in my research group currently. Ones in blue are former members of my research group, and others in black are colleagues at other institutions. So a little bit of a brief outline of what I'm going to be talking about today. First, I'll give a little introduction of why we want to understand turbulence in astrophysical plasmas, and I'll cover a little bit about models of the turbulent cascade and proposed mechanisms that dissipate the energy in turbulence. And then I want to focus on what exactly do we want to predict. And we want to predict that in terms of the dimensionless parameters that control the turbulent heating. And I'll review existing turbulent heating models that are out there. And then I'm going to turn to our approach of how to solve this problem and move on to improved models using something called the field particle correlation technique that my group developed from kinetic plasma theory to identify the dissipation mechanisms and quantify the heating associated with them. And then I'll show applications of that technique to both numerical simulations of turbulent plasmas as well as in situ spacecraft observations. And finally, I'll just very briefly touch on ideas to use machine learning to automate the identification of the different mechanisms that actually serve to dissipate the turbulence. And I'll conclude by proposing a new strategy to develop improved predictive models of turbulent heating. So why do we want to study plasma turbulence? Well, at the very base, the plasma heating that occurs in space and astrophysical plasmas is often caused by the dissipation of turbulence. And in detail, this plasma heating occurs down at very small scales, microscales, which a lot of astrophysicists don't like to think about. But in fact, that heating can feed back on the system and influence both the mesoscale and macroscale evolution of that system. So this really is a problem of multi-scale physics. It's some of the hardest kind of problems to approach, both numerically and theoretically. And so in sort of conclusion, identifying these physical mechanisms that govern the turbulent dissipation and then quantifying the rate of heating associated with each of those mechanisms and how they heat the different plasma species is really crucial to our understanding the evolution of these systems. So to turn to an example that is probably near and dear to many people here's hearts is the idea of black hole accretion disks. And up on the upper left, there's a sort of artist's depiction of what a black hole accretion disk might look like. And in this system, of course, we know that matter spirals into the black hole and converts a tremendous amount of gravitational potential energy into heat. But it does this via several processes. First, in that differentially rotating accretion disk, the magnetorotational instability can drive turbulence. And down here on the lower right, there's an old simulation from Bulbus and Hawley of turbulence being driven in an accretion disk. That turbulence then cascades energy nonlinearly down to smaller and smaller scales until it reaches sufficiently small scales that kinetic plasma physics mechanisms can damp that turbulence and lead to the plasma heating. Why do we care about all of that? Well, we care about it because the radiation that's emitted from that accretion disk plasma is a strong function of the plasma heating. So if we want to interpret X-ray observations of black hole accretion disks, it requires that we understand the kinetic plasma physics and the resulting plasma heating due to the dissipation of turbulence. And of course, a great example of this is the Event Horizon Telescope image. This is that first image in 2019 of M87. We want to be able to interpret that and understand it. You have a question?
Yeah, just to anchor me so I don't get lost after the first slide. Can you just tell me just physically what do you mean by kinetic mechanisms?
Kinetic mechanisms.
Just shorthand.
Yeah. Basically, it means that the plasma is weakly collisional. So you have a 6-dimensional phase space. It's not just a fluid model like MHD, but you actually have things like collisionless wave particle interactions, which are actually, and I'll spend a lot of time talking about this, so hopefully it'll make it clear, that are the mechanisms that actually damp the turbulence. It's not viscosity and resistivity, which are fluid limits that are really not applicable to most space and astrophysical plasmas. You're welcome. Okay, so why do we need this? Why do we care, right? Well, so here's an example of a general relativistic radiative MHD simulation of Sagittarius A star. And what we have is we have two simulations. They're identical simulations with one difference, which is they're using a different prescription for how the dissipated turbulence, when that turbulence dissipates, where that energy goes, whether it goes to the ions and the electrons, and what the nature of that heating is. So on the left side, they've used a turbulent heating model that I developed back in 2010 that is basically trying to look at the dissipation of a large turbulent cascade. And on the right is a heating prescription that was developed based on the physics of transrelativistic magnetic reconnection that heats. And as you can see, there's a dramatic difference between these are sort of simulated emission from that. This is what it would look like. If you could resolve that system, this is what you would see, the light emitted from it. And on the left, that turbulent system, that outflow that you see along the axis really lights up bright, and in the reconnection simulation you just don't see that at all. So this really makes a huge difference. And if we take something like an EHT observation and we want to interpret what we're seeing, well, we really need to understand what kind of heating is going on there. So that's the big motivation there. Now, to get to your question about kinetic plasma physics, is that for most of space and astrophysical plasmas, the dissipation occurs on length scales where the plasma dynamics is weakly collisional. So although magnetohydrodynamics, or MHD, can accurately describe the plasma behavior of the turbulence at very large scales, by the time that turbulence gets down to quite small scales where the dissipation mechanisms act, the physics that governs that dissipation is well beyond the scope of the MHD description. You simply can't describe it using MHD. So the physics of dissipation is controlled instead by the kinetic plasma physics. And so we need to use a kinetic plasma physics treatment of the turbulent dynamics and its dissipation to resolve what those actual physical mechanisms are that remove energy from the turbulence and transfer it to the plasma, either the particles, the ions, or the electrons. So let's turn to models of the turbulent cascade and what the proposed mechanisms of dissipation are. So here's an example to start a little closer to home. This is the solar wind turbulent magnetic energy spectrum. So if you take a spacecraft and you fly it up, you get outside of the magnetosphere, out beyond the bow shock into the free solar wind, and you measure the magnetic field fluctuations as a solar wind is streaming by your spacecraft at 500 kilometers per second. You have a time series of magnetic field measurements. You Fourier transform that, and you generate something that looks like this. This is a magnetic energy frequency spectrum. It extends over 7 orders of magnitude. And there are a number of interesting features here. We've got several breaks at the very lowest frequencies. You have an f to the -1 spectrum, and then there's a break, and then it steepens to what is approximately f to the -5/3. This we interpret as the turbulent inertial range, and I will explain more what that means as we go forward. And then it breaks again at frequencies that are a few tenths of a hertz, and it gets even steeper with f to the -2.7 or 2.8 spectrum. And we want to be able to understand both what is the dynamics behind all of this, why does this spectrum look like this, and this is an incredibly clear example of there's a lot of physics underlying this. We want to know what that is. So as a theorist, you know, we don't usually want to talk about the time scales, and we convert this into a magnetic wave number spectrum by assuming what is called the Taylor hypothesis, which is assuming that if I measure time variations in the magnetic field, what I'm really measuring is spatial variations in the plasma as it's streaming by our spacecraft at 500 kilometers per second. So I can use that Taylor hypothesis to transform this spectrum into a magnetic energy wave number spectrum. And then we can interpret these various breaks here as some physical length scale that's associated with the system. So at the very largest scales, where now the spectrum goes like k to the -1, you have what's called the energy containing range. And in that range, it's essentially unevolved turbulence. It hasn't had chance to interact and transfer its energy to smaller scales. I won't go into that. It's not really relevant to the astrophysical case. But then at a scale of about 1 million kilometers, that's where the interactions of turbulence start to play a role. And it starts to transfer energy from large scales, scale by scale, down to ever smaller scales through what's called the inertial range, where there's no dissipation. It's just a steady rate of energy transfer from large to small scales. And then it reaches down to the ion scales. This is a scale of approximately of the ion Larmor radius of about 100 kilometers. And at that point, the spectrum has another break and it steepens to about K to the minus 2.8. And then you get down to the electron scales at 1 kilometer, and everything at the ion scales and below we call the dissipation range. And this is where we expect most of those dissipation mechanisms to act. So what we want to do is we want to understand this flow of energy from these large scale turbulent motions down to small scales where they can be converted to plasma heat. And we want to understand how that turbulent energy is transferred into heat of the plasma species. So to give you a little bit of a cartoon of how this works that's a little bit more dynamic is here we have a system, and I'm now going to normalize my magnetic energy spectrum by the ion Larmor radius scale. So this is the ion Larmor radius scale right there. And at scales that are larger than that, and in the solar wind, it's about 4 orders of magnitude, that is what we call the inertial range. And the spectrum there tends to go something like K perp to the minus 5/3. Now, the perpendicular component of the wave vector arises from modern theories of anisotropic plasma turbulence. Again, that's a bit beyond the scope of my talk here, but nonetheless, that's the theoretical interpretation. And then at smaller scales below the ion Larmor radius scale, we have what's termed the dissipation range. And again, the spectrum there goes something like K perp to the minus 2.8. What happens is that at this largest scale, something injects energy into the turbulence. So, if you're doing a turbulence simulation, you drive it at the largest scales, those fluctuations interact and they transfer energy successively to smaller scales. So these nonlinear interactions transfer energy scale by scale in sort of a local energy transfer to smaller scales. And through this whole inertial range here, there's no loss of energy. That's actually the definition of the inertial range. There's a steady state transfer of energy from large to small scales with no loss of energy. And that is all happening at scales that are larger than the ion Larmor radius. This is the regime where MHD is applicable. And so all of the fluctuations there are primarily Alfvén waves. Then as you get to smaller scales, we get into what is called the dispersive regime. Once you get to scales below the ion Larmor radius, the Alfvén wave transitions into the kinetic Alfvén wave, or KAW, and those are dispersive waves. So the smaller the perpendicular wavelength, the faster they propagate. Now at these ion scales, what you can get are kinetic mechanisms, things like collisionless wave particle interactions, Landau damping, transit time damping, or cyclotron damping that can remove energy from the turbulence at those scales, but they don't remove it all. So some of that energy keeps going and keeps cascading down as a cascade of kinetic Alfvén waves. And as it goes further and further, the electron damping gets monotonically stronger and stronger until eventually it's strong enough to completely remove the energy from the turbulence and give it to the electrons. And you've terminated the turbulent cascade. And so you have sort of a weakening nonlinear energy transfer in this regime. And in addition, and I won't go into this too much, but you also tend to find current sheets that arise at those scales quite frequently when you're looking at things like spacecraft measurements or turbulence simulations. So what are the dissipation mechanisms? I haven't talked about that yet. What are the proposed dissipation mechanisms? I'm going to focus first on non-relativistic case for turbulence, but we are focusing on weakly collisional turbulence. So the first class of mechanisms are resonant wave particle interactions, things like Landau damping, which is essentially particles that are surfing on the parallel component of the electric field, that the waves have some electric field associated with them, and particles can just gain energy, just like surfing on a wave. And then there's something called transit time damping, which is the magnetic analog of Landau damping. In other words, because you're in a magnetized plasma, particles are undergoing cyclotron motion. They have a magnetic moment associated with that motion. And fluctuations in the magnetic field magnitude can accelerate that magnetic dipole via the magnetic mirror force. So you get collisionless damping in that way too. And you can also get ion cyclotron damping as well. So that's one class of interactions. Another are non-resonant wave particle interactions. So things like stochastic ion heating, magnetic pumping, and also what we call viscous heating, but really it's at high plasma beta, plasma beta being the ratio of the thermal to the magnetic pressure. At high plasma beta, temperature anisotropy instabilities can be triggered by compressions in the plasma, and those effectively look a bit like a viscosity that can damp the turbulent motions and remove energy. But that one actually happens at fairly large scales rather than all the other mechanisms, which more or less happen at small scales. And then the final class of mechanisms are dissipation in the current sheets that we observe via collisionless magnetic reconnection. So there are also a number of people here at the Flatiron Institute and at Columbia have been very busy studying and doing excellent work in relativistic turbulence. And you have a similar sort of characterization, although it's been much less studied than the non-relativistic case. So one can again have resonant wave particle interactions. And Eunice had a fantastic paper last year where he did simulations and saw that this non-relativistic paraplasma turbulence was being dissipated by Landau damping and leading to parallel energization of the particles. You can also have non-resonant wave particle interactions, that same viscous heating triggered by temperature anisotropy instabilities at high beta. And finally, you can get non-thermal acceleration by reconnection. And I know that Vladimir Zhidankin and also Luca Comiso at Columbia have done a lot of work on this recently, seeing that reconnection can occur in these paraplasmas and lead to non-thermal acceleration of particles that then, of course, damps the turbulence. Now, that's about most of all that I'll talk about relativistic turbulence. This talk is going to focus mostly on non-relativistic turbulence, but I just wanted to touch base with that because, of course, that's of great interest to people here as well. So turning away from that, we would say, you know, what exactly do we want to predict? I said we want predictive turbulent heating models. What do we want to predict? What is the information that we need? So we know that the dissipation of turbulent energy eventually is going to lead to heat the plasma. So what is it that we want to know? So first of all, there's of course a rate of the dissipation of turbulent energy. And that should, if it's in some kind of a steady state, be equal to the turbulent cascade rate. So energy is injected in the turbulence, it cascades down to small scales, and it's going to be dissipated. So there's some rate of dissipation called Q. But we don't just want to know that. We want to know, because this is a weakly collisional plasma and the ions and the electrons can have vastly different temperatures, how is that dissipated turbulent energy partitioned by species, by ions or electrons? And then finally, we can go further and say, what is the nature of that energization? Am I energizing the perpendicular degrees of freedom or the parallel degrees of freedom? Because those have very different observational consequences. And so if we want to define some quantities that we need to develop from this model, we want to develop, of course, the total rate of turbulent dissipated energy. We want to look at, say, the ratio of ion to electron dissipation. And then we want to look at sort of the anisotropy of that dissipation for each of the species. So each of these quantities in the red boxes at the bottom are basically the quantities that you can use as a sub-grid scale model for turbulent heating that can be attached to large-scale simulation codes, things like that general relativistic MHD code of a black hole accretion disk. So you can use that to determine, and that's exactly what was done to generate those two different pictures. And I will say, of course, here that turbulence can also lead to the acceleration of particles to high energy, particularly in the relativistic case. And again, I'm not going to spend more time talking about that today, but that is another destination where some of this turbulent energy can go. So how does the turbulent energy affect the evolution? I said that this is a multi-scale problem. It can affect the large-scale system and other things that we care about as astrophysicists. So the total turbulent heating can influence a macro-scale evolution of the system. So this is, of course, a manifestation of the multi-scale physics that exists. And an example are the thermodynamics of galaxy clusters, which depend partly on the heating of the intercluster medium. And you can get examples of things like cooling flows that are important, that we need to really understand the turbulent heating to get a full understanding of that thermodynamics. Similarly, the observed radiation is going to depend strongly on which species is heated. So if the electrons are heated primarily, they really are going to radiate their dissipated turbulent energy much more easily than the ions will. And so this is the example of, say, radiatively inefficient accretion flows, where if you dump a lot of energy in the ions and they fall beyond the event horizon, well, you never see that energy again, and there's no observational emission that we can see from that. So it has a significant observational consequence. And then finally, the radiative processes also depend on the nature of that plasma heating. So synchrotron heating requires that you heat the particles perpendicular to the magnetic field. If you just heat them parallel, you won't see that. And the example here is, again, the damping of relativistic alphenic turbulence that Yunus has published last year, where he saw that it was simply heating the particles, the pairs, in the parallel direction, and that would lead to very little synchrotron emission. And the emission that you would see from that heated plasma would actually then be dominated by inverse Compton scattering rather than synchrotron heating. And that will give you a very different prediction for what frequency spectrum you should expect to see. Okay, so what are the requirements for a turbulent heating model? If we want this to be useful, this turbulent heating model has to predict the plasma heating in terms of what I'll sort of quote as observable parameters. Now, these aren't necessarily observable in the sense that, of course, we know that, you know, if you want to understand the ion or electron temperature in some far off, you know, system, or what's the magnetic field strength, you know, you've got to interpret that from various different things, Faraday rotation to look at the magnetic field, et cetera. So it may not be exactly directly measurable like it is with, say, an in situ spacecraft where you can directly measure the fields and the particles. But nonetheless, it's a large scale parameter that at the very least, we can make a good theoretical argument for what sort of range of values we expect. So we want to know that. And the physical mechanisms that will remove the energy from the turbulence and energize the plasma particles, they're going to depend on both the plasma parameters, things like the plasma beta, the ratio of the thermal to the magnetic pressure, or the ion to electron temperature ratio, as well as the nature of the turbulent fluctuation. So there is a set of turbulence parameters that will depend on. So these physical mechanisms then will damp the turbulent fluctuations, and they will control which species are heated, the partitioning of energy, as well as whether they're heated in the perpendicular or parallel degrees of freedom, again, which has a significant observational consequence. So it's really critical to identify those physical mechanisms that damp the turbulent fluctuations. So I want to turn a little bit to what are the dimensionless parameters that actually control turbulent heating? And there are a lot of them. So and again, here I'm just going to focus on the case of non-relativistic turbulence. So as I said, there are plasma parameters upon which these turbulent dissipation mechanisms will depend. The most important one by far is the plasma beta. And in this case, we're going to be very particular and define it as the parallel ion plasma beta. So it's the parallel thermal pressure over the magnetic pressure, okay? A second parameter is the ratio of the ion to electron temperatures, and we'll specifically focus on the parallel temperatures here, okay? Two more parameters are the ion temperature anisotropy and the electron temperature anisotropy. And then finally, there is a dimensionless measure of the plasma mean free path. How far do the particles go before they scatter compared to the, you know, the length scale of the turbulence at the driving scale. So there are 5 plasma parameters that matter that will tell you a lot about what the different dominant dissipation mechanisms may be. That's just the plasma parameters. There are also turbulence parameters that depend on what are the actual fluctuations. So there's a measure of the driving scale. And here again, I've been very precise to define the perpendicular scale of that driving of the turbulence. So the naught subscript means the driving scale. So there's the perpendicular driving scale as well as any anisotropy in the way we're driving. So we might drive something where the fluctuations have very long parallel wavelengths and very short perpendicular wavelengths. Or we might drive it in an isotropic way where both those wavelengths are the same. And then there's the nonlinearity parameter. This is really just a measure of the strength of the turbulence at the driving scale measured as a function of the perturbation of the magnetic field over the background magnetic field. So it's kind of delta B over B, but there's also some of that anisotropy included in there. And it effectively, this parameter tells you the strength of the nonlinear reactions over the strength of the linear terms in the equations of evolution. That's where this it derives from, originally from Goldreich, Schrieder, 95. And then in addition, there's the compressibility ratio. You can have completely incompressible fluctuations like alphenic turbulence, or you can have an admixture of compressible and incompressible fluctuations where you've got some contribution from fast and slow magnetosonic wave modes. And then finally, there's something called the imbalance ratio. So turbulence is often thought of as in a plasma as nonlinear interactions between alphane waves that are propagating up and down a magnetic field. They pass through each other, distort each other, and that is effectively what transfers energy from large scales down to smaller scales. In something like an MRI accretion disk, you don't expect there to be any difference between waves going up and down the magnetic field. But in the heliosphere and the sun, like at the solar corona, there's lots of wave energy moving away from the sun and very little wave energy moving towards the sun. And that has significant implications in terms of how the turbulence will evolve and what the dissipation mechanisms will be, in particular in light of something recently that was discovered just in the last couple of years called the helicity barrier. And again, that's a bit more of a space physics, heliophysics topic, so I won't delve too far into that, but it is one of the parameters. Yes?
Are those parameters enough to capture like Pearl in the driving, like, or is this just, yeah, is the driving just considered like sort of standard compressive driving?
Yeah, I mean, okay, so I mean, you know, we could go on forever. I mean, there can be, you know, helical driving as well in a system, and that's actually not in these parameters. But you know, in a lot of the systems that I'm looking at, I mean, if you want to look at dynamo action in, say, you know, the solar convection zone or something, then you would need to include that as well. That's not kind of one of the things that I tend to focus on, so I don't tend to worry about that too much, but that could indeed be an additional parameter. I mean, in some ways there is like an infinite number of parameters, but even here, you know, I have got 10 parameters. Trying to model anything in a 10-dimensional parameter space is a near impossible task. So what we often do is we simplify things. So if I take some simplifications, and it's going to sound crazy if I say it's a weakly collisional plasma, it's incompressible turbulence, it's a strong turbulence, and it's balanced with isotropic temperatures and isotropic driving. That sounds like a whole lot of approximations, but in fact, many turbulent systems will satisfy all of these characteristics. And in that case, you can simplify this down, and you just have the standard ion plasma beta, which is the ion thermal pressure over the magnetic pressure, and the ion to electron temperature ratio. And those are the only two plasma parameters left. And then you've got the driving scale of your turbulence. You've assumed it's isotropic, so there's just one scale here. And you've got the nonlinearity parameter, how strong you're driving the turbulence. So now you're down to four parameters, and it makes things a lot more tractable. But of course, you know, in a given system, and you know, even a, you know, something like a dynamo system, you might need to characterize something like helicity. But in a given system, you may need to add one or two of the other parameters to say, you know, that the temperatures are anisotropic, and so you've got to include that physics. But we can certainly have a series of models that have different detailed treatments of the physics involved. Okay, so I want to briefly review. Yes, go ahead.
Could you briefly say something about the incompressible aspect? What type of systems would that be?
Well, if you look out in the solar wind, for instance, and you just go outside the Earth and you measure the fluctuations, about 90 to 99% of the energy is incompressible. It's all contained in alphenic fluctuation, alphane waves. And there's a very small component of slow magnetosonic fluctuations. There's almost no fast magnetosonic fluctuations. So that's an example where, you know, this compressible to incompressible ratio is basically zero. But in a lot of cases, I mean, it's actually quite hard to compress a plasma, but it's really easy to shake a plasma and generate alphane waves. So in many cases, what you get is you get much more incompressible fluctuations than compressible ones. You know, in MRI turbulence, very recently in the last sort of year or so, there have been some careful studies, and they found that ratio is actually about 50-50. So it's about 1-to-1, but it's rarely really dominated by compressible fluctuations. It's sort of almost at least half, if not, you know, 100% incompressible. Okay, so turning to reviewing some existing turbulent models, and I'm not going to spend a lot of time on this. So there's a model that I developed in 2010, and it's a model that's based on non-relativistic, incompressible, balanced, strong turbulence. And all of the damping is due to the Landau resonance. So either Landau damping or transit time damping. And what it gives you is it gives you the ratio of the ion to electron heating rates as a function of that ion plasma beta and that ion to electron temperature ratio. So in that simplified version, this gives you something very valuable. There was another model by Ben Chandran of the University of New Hampshire where he included another effect. He included stochastic ion heating. So it looked very similar to the Howes model, although it didn't involve a turbulent cascade. They just looked at what are the damping rates at the ion scales and what's the ratio of heating by one mechanism or another. And they came up with a different prescription that actually gave you the ion parallel and ion perpendicular heating separately. And then whatever was left over was the electron heating. And so it's a function of the beta, the temperature ratio, and also this, which is not the way I would characterize things, but it's the amplitude of the turbulent fluctuations at the ion Larmor radius scale relative to the thermal velocity. That's just the way his model defined that parameter. But it is a dimensionless parameter that you can characterize things with. But this, I would say, is not a large scale parameter. It's like you really have to have very detailed measurements to know what that is. So kinetic simulations can do it, but observations, particularly astronomical observations, can be very hard to determine what that number is. And then more recently, in the lead up to trying to interpret Event Horizon Telescope observations, Rowan et al. Developed a model for heating based on the physics of trans-relativistic magnetic reconnection, which is, again, it gives you the ratio of the electron heating to the total heating. And it's a function of the plasma beta and sigma W here, which is the relativistic magnetization parameter, which is essentially the magnetic energy over the rest energy of the plasma, more or less. And then finally, there was a model in 2018 by Kawazura that was based on a suite of hybrid ion gyrokinetic simulations with isothermal electrons. And it's very similar in some ways to this Howes model in terms of the approximations that have to be satisfied. And in fact, this model more or less verified at least the qualitative features of the Howes 2010 model with some minor, minor quantitative adjustments, but it is more or less verified that. And then more recently in 2020, they actually did a model with some compressible driving and were able to modify this to include the effects of a varying amount of compressible driving as well. So to give you a sense of what one of these models actually looks like, I'll show you my Howes 2010 model. So this was published in Monthly Notices back in 2010. And what it does, it assumes that you're driving it at large scale, that you're driving it here. This nonlinear parameter of 1 means that you're driving strong turbulence. There's no compressible fluctuations and it's balanced turbulence. Again, lots of systems satisfy these requirements. And again, it's based on a balance between an analytical model of the turbulent energy cascade, and it assumes that all of the dissipation is associated with collisionless wave particle interactions via the Landau resonance, specifically Landau and transit time damping. And what it gives you is the partitioning between ions and electrons as a function of beta and Ti over Te. So over here, I have plotted as a function of plasma beta, which is the most important parameter by far, what that variation looks like as a function of beta and for 3 different temperature ratio values. And so, of course, you can see the temperature ratio doesn't make a big difference, but the beta sure makes a huge difference. I mean, orders of magnitude there. And the actual model is this. I mean, this is what it looks like. And so if you have the ion plasma beta and the temperature ratio, you can compute these values. And it basically gives you, it's the red dashed lines up here, whereas the the red dotted lines, the black dashed lines are the actual model results, and the red dashed lines are sort of a fitting to that. So that's what it is. And as I mentioned, that Kawazura model, which is based on a suite of gyrokinetic simulations, these are the results of those gyrokinetic simulations. And what they really saw was that, the form of these curves really, qualitatively looks very similar to that analytical model that I developed. And there are just some relatively minor quantitative changes between those. So a question is, how do we actually go about developing improved models that are better than these? Well, again, as I've said many times, the weakly collision law dynamics governs the mechanisms that remove energy from the turbulence and energize the particles. So it's kinetic plasma physics that we have to deal with this. We can use kinetic simulations to drive our understanding of this, but we can also use in situ spacecraft observations, because I spend a lot of time working with space physicists. So there are two key tasks we have to do. Number one, we have to identify the physical mechanisms that damp the turbulence. And number two, we have to quantify the heating of each plasma species by those mechanisms. And we want to do both of these as a function of those plasma and turbulence parameters that I went through before. So the recently developed field particle correlation technique, which my group developed about 7 years ago, provides a feasible way to actually do this and to accomplish this. So for the next sort of 20 minutes or so, I'm going to cover this technique, which is derived from kinetic plasma theory, and then show its application to actual turbulent systems, both simulations and spacecraft observations. So the weakly collisional plasmas are governed by the Maxwell-Boltzmann equations of kinetic plasma theory. So we've got a Boltzmann equation for each species, and that evolves a distribution function in 3D, 3V phase space. So this is a 6-dimensional phase space, 3 dimensions in physical space, and 3 dimensions in velocity space, as well as time. And this system is closed by Maxwell's equations, which give us the electromagnetic fields in terms of the current density and the charge density. So on the time scales of turbulent dissipation, if you're weakly collisional, this collisional term really doesn't play much of a role. So we can throw that away, set it to 0, and it returns this equation to what's called the Vlasov equation, the left-hand side just equal to 0, okay? And it's this term, this Lorentz term here, this is the Lorentz force, E plus V cross B over C, that is responsible for the interactions between the fields and the particles. So that's the thing that's actually going to do work on the particles and energize them. So if we take those Maxwell-Boltzmann or Maxwell-Vlasov equations, we can combine them to derive a conserved Vlasov-Maxwell energy, which includes the electromagnetic field energy as well as the total microscopic kinetic energy of the particle species, where I've defined the particle energy as this integral of 1/2 mv squared times the distribution function, integrated over velocity and integrated over volume. Now, what we want to learn is, what is the rate of change of particle energy? That's the particle heating, that's the particle energization. And so if we take the time derivative of this, that ddt can go right in through all of this. The only thing that depends on time is the distribution function. So I can put it right in there. So what we're doing is we want to measure the change in the particle energy by using changes in the distribution function. Now, I know df dt is governed by the Vlasov equation. So I can replace that df dt with the rest of the Vlasov equation. And what I get is an expression that looks like this. Okay, now this equation has 3 terms, but the last term, which is the effect of the magnetic fields on the particle energy, is 0 when you integrate over velocity space. It's simply a consequence of the fact that magnetic fields can do no work on particles. Furthermore, this term, which is an advective term, really just describes the energy that's moved around. As you move plasma from one place to another, you're moving its kinetic energy from one place to another. But if you integrate over the whole volume, you're just moving energy from one place to another. You don't change the energy. So it's a perfect differential when integrated over velocity space, and it gives you 0. So it's this electric field term that does the work on the particles. So to determine this, we could get the rate of change of particle energy by just calculating this. The problem is, this is integrated over velocity space, which is not too much of a problem, but also over all physical space. And this is not something that's observationally accessible. And so, the motivation for developing this technique was to use it with spacecraft observations, where you have one or at most a few points where you have measurements. You can't integrate over all space doing that. So in order to maximize our use of the information that you can measure, is what we do is we define something new. It's called a phase space energy density. It's just 1/2 mv squared times the distribution function. So this is an energy density that's a function of that 6-dimensional phase space. and something that you're probably not familiar with. And so if I take the Vlasov equation and I multiply it by 1/2 mv squared, I get an equation for the rate of change of this phase space energy density. Now, I can interpret each of these terms, which I already did. This first term is the advection of particle energy, as I've said. And that actually gives rise to the pressure forces in fluid theory. This final term is, of course, the work done by the magnetic field, but it integrates to 0 over velocity space. And again, we're going to focus on this work done by the electric field, and it is responsible for the net change in the particle energy. I'm going to skip this next equation because it's not that important. Okay, so here's the question. How do we exploit this information to understand what's going on in a system? So I'm going to give you an example of the Landau damping of a single kinetic Alfvén wave. Okay, so if you've taken a plasma physics course, you know that if you take a velocity distribution, which is Maxwellian, this black dashed line here, okay, and you put a kinetic Alfvén wave in it and it Landau damps, quasi-linear theory tells you what's going to happen is it's going to flatten the distribution function right around the parallel phase velocity of that wave. And that's exactly what it does. Okay. In fact, this looks like a diagram, but it's actually simulation results, but that's not that important. But the point is it flattens that distribution function. So what do we do here? Well, what I want to do is I want to evaluate this term. So I define what I call the field particle correlation, because I've got the particles in the distribution function, the fields here. I'm going to focus on the parallel component because that's what mediates Landau damping. So it's a parallel contribution to this dot product here. So I've got this term. So what I can do is I can evaluate this term as a function of parallel velocity and also as a function of time vertically. Okay. And if I do that, I will get, and this is actually simulation results, I will get a picture that looks something like this. There's sort of oscillation. Red is transferred to the ions, blue is transferred from the ions via the parallel electric field, and you get that. So what is this signal telling me? So it's a bit hard to interpret. Well, there are two parts to the signal. The first part is a conservative transfer of energy between the fields and the particles. And this is just associated with undamped wave motion. If you have an Alfvén wave, you get kinetic energy pulls the plasma up, stretches out the magnetic field. It transfers that kinetic energy into magnetic field energy, and then that stops the motion. And then that magnetic field is bent and it wants to straighten out. So it rebounds and it reaccelerates the plasma. So there's constantly energy being transferred back and forth between fields and particles. But that's not what we care about. That's not changing the energy of the particles in a secular way. But indeed, there's also a second piece, which is the secular energy transfer associated with collisionless damping. So if I take a slice vertically in time, just at one particular velocity, and I plot it as a function of time, I get this function that's oscillating up and down. Well, if I take that oscillating function and average it over a sufficiently long time, it flattens out to something. And although the oscillations are very large, the net average of that is not zero. And that's the secular energy transfer. That's the net transfer of energy to the particles that's associated with damping the wave. And it's changing the particle energy. So what do I do? How do I do this? Well, I have this system where I've taken that correlation. What I do is I specify a correlation interval where I'm going to take a time average over that time to eliminate all that oscillatory transfer. And so here I can take just a wave period as the ideal case for a single wave. And when I do that, I get a signal that looks like this. Okay, and this is what I call a time stack plot. It's the rate of change of energy to the particles as a function of particle velocity and time. And what I see here is the vertical dashed black line is the resonant phase velocity of that wave. And what I see is blue represents a loss of energy. The particles are losing phase space energy density, and the red is a gain of phase space energy density. This is what we call a bipolar signature. But in fact, that bipolar signature is simply the manifestation of this quasi-linear flattening. Because if I look at what is the ion phase space energy density, well, it's 1/2 mv squared times F. Okay, the only thing that changes here is F. That's the only thing that changes. V is a coordinate in kinetic theory. It does not change. And so what happens is if I lose energy here, that F has to drop down. And if I gain energy above the velocity, that F increases. That is the flattening. So this bipolar signature is simply a manifestation of that quasi-linear flattening associated with the damping of that wave. So I can show you what this looks like in a proper simulation. So if I take a single kinetic Alfvén wave, it has ion plasma beta of 1, temperature ratio of 1, K per rho I of 1.3. And now I'm plotting this as a function of gyrotropic phase space. So I've got three-dimensional phase space. And it's a magnetized plasma. So what I'm going to do is I'm going to treat that phase space in a cylindrical coordinate system where the axial direction is the direction of the magnetic field. And what I do is I average over the azimuthal component. And so now I have a function as a function of v parallel, the axial velocity, and v perp, the radial velocity. So this is what we call gyrotropic phase space because you've averaged over the gyro phase. And what I see, and this is a simulation result, you see this very, very clear bipolar signature that is associated. And this is what we call the velocity space signature of ion Landau damping. And it enables you to say, I know exactly what is going on here because I'm using all that information to identify the mechanism that's dissipating the turbulence. I can do the same thing and I look at the electrons. Now, because the electrons are, 1,800 times less massive than the ions, their thermal velocity is 40 times larger, meaning that that phase velocity is way down near zero when normalized to the electron thermal velocity. So if I zoom into this picture, I can see that in fact, I am seeing an energization of particles just above that phase velocity. It gets a little cut off by zero here, so you don't see the negative part as much. But this here is a velocity space signature of electron Landau damping. So what do we learn from this in this? We want to define a technique where we can do this. And this is the field particle correlation technique. So again, we're going to focus on this electric field term. And what we do is if we have measurements at a single point in your simulation or out in space, where we're going to compute a correlation of the electric field at that position and the particle velocity distribution function, and we're going to average it over some correlation interval. So we define the field particle correlation. This is the parallel field particle correlation for the parallel part of that dot product. And it looks like this, and it's averaged over some time length. Now, depending on the problem, you can also do correlations with the perpendicular component of the electric field, or I do stuff with collisionless shocks as well, and we just use all three components, X, Y, and Z, and just keep them separate. So what is the insight we gain from the field particle correlation technique? First, we can distinguish and identify the kinetic energization mechanisms through their unique velocity space signatures. And so here we see this bipolar signature of Landau damping. And second, we can actually determine the rate of change of the spatial energy density. So if I take this is dw dt, well, the integrand here is just that field particle correlation. And if I integrate over that velocity space, I can plug in that field particle correlation. I can do an integration by parts here, and I can show that it's equal to that. But Q v parallel F integrated over velocity is just the parallel component of that species current density. So this is just J parallel E parallel. So by doing an integration over velocity space, I can determine the rate of work done on species S by the parallel component of the electric field. So it both lets you identify the mechanism and quantify the rate, which are the two things we're trying to do here. So let me show you some applications to actual plasma turbulence simulations and observations. So again, touching base, we have this magnetic energy spectrum in the solar wind. And as I've said, we've got these three different classes of of proposed dissipation mechanisms. And the key point here is that the velocity space signature of each of those mechanisms gives you a way to identify and distinguish those mechanisms. So let's have a look using numerical simulation. So first, our first test of this in a turbulence simulation was a gyrokinetic simulation of turbulence, weakly collisional turbulence with beta 1, temperature ratio of 1. The turbulence parameters, it was anisotropic, and it was in critical balance. So this is a case of strong plasma turbulence. And so if I go to somewhere in that simulation box and I plot the perturbed distribution function, so if you say the equilibrium distribution as function is Maxwellian, I'm just going to plot the perturbation from that, I get something that looks like this. Well, I can't make heads or tails of that. Okay, well, I can take this thing and I can compute that field particle correlation, right? That whole form of df dv times e parallel, et cetera. And I get this. Again, doesn't really tell me much, but I haven't averaged it over anything. This is just instantaneous. It's a mess. And it really just reflects the fact that in the turbulent plasma, there's a whole lot of things going on at once. But if I take that and I average it over a period that is sufficiently long, I get a really nice clean signature of that. And this, I see that very nice bipolar signature here. And this shows evidence that Landau damping is actually occurring to dissipate the turbulence. There is actually a secular transfer of energy from the turbulent fluctuations to the particles. And we can see the parallel phase velocity, or these dashed lines here, it's right hugging that parallel phase velocity. So this really is a signature of Landau damping. And it actually showed, it had been conjectured that in turbulence, Landau damping wouldn't work because all the turbulent fluctuations would interrupt the fact that the particles have to stay in phase with the wave for a while. But in fact, that doesn't work. It really does happen even in a turbulent plasma. Now, as I've said, I can use this to distinguish energization mechanisms. So I can look at lots of those different proposed mechanisms. So we've seen the case for Landau damping, where I've got that bipolar signature. We can also do transit time damping. Again, that's the magnetic analog of Landau damping. It goes to 0 down here. It's still associated with that parallel phase velocity because it's Landau resonant, but it looks qualitatively different from here, and you can distinguish those. You can also look at cyclotron damping. So this was a hybrid Vlasov-Maxwell simulation of high frequency turbulence, which led to a lot of ion cyclotron damping. And you see energization in a completely different part of this gyrotropic phase space. So you can completely distinguish those. And then there's a Pegasus simulation. And in fact, and I will decompose this in a minute, we see evidence for 3 different mechanisms going on here. I'll cover that in the next slide. In addition, we've done analytic models of, say, magnetic pumping, one of those non-resonant mechanisms. And again, we get yet a different pattern from all of these above. And then finally, I can look at electron Landau damping. This is actually from a spacecraft observation. And what we see again is this bipolar signature about what turns out to be the resonant velocity for kinetic alphane waves in this system. So to look at this Pegasus simulation, this was Matt Coons' hybrid simulation. We actually look at this. Well, this thing looks like a bit of a mess, but from theoretical reasons, you can actually decompose this. And all of the energization that's happening down here that's very strong, and it's all below 1 thermal velocity in perpendicular energy, that's stochastic ion heating. And this was early in the simulation, and this was later in the simulation. Later in the simulation, that the core of the distribution flattens and the stochastic heating shuts off, and it's just gone, completely gone, okay? Up here, this segment here is actually ion cyclotron heating. It's in the same place as that other ion cyclotron case I showed, and that's still operating late time in the simulation. And then there's also this sort of vertical bar, which is actually even more apparent here, which is the signature of transit time damping. And then in the parallel case, you can actually see the signature of Landau damping as well. So you actually see 4 different mechanisms happening all in the same simulation. But even more important than this, we can go to ground truth and look at spacecraft observations. So we have MMS observations. So the magnetospheric multiscale mission is 4 spacecraft that are flying around and sampling near Earth space. So this is the Earth's magnetosphere. This is the bow shock out here. The solar wind is coming in. Once the plasma, the solar wind plasma has passed through the bow shock, it becomes extremely hot and turbulent. And this is what's called the magnetosheath region. And so we looked at a region in in space where we're in the magnetosheath. And these are direct measurements from the spacecraft of the fields and electron velocities as a function of time. The plasma parameters for this particular interval, beta I, was 0.8. And this plasma tends to have very high ion temperatures. So Ti over T was 10. That's pretty typical of the magnetosheath. And so we were looking actually at the electron field particle correlations. If we look at the velocity distribution in this gyrotropic phase space here, we see the equilibrium here looks very Maxwellian. It's very, smooth and circular. But if we take the perturbation to that and correlate it with the parallel electric field, we see these bipolar signatures that arise. And I can take this gyrotropic signature and integrate it down over V perp, because there's not a lot of structure this direction other than it just dropping off exponentially. All the structure is along the V parallel. So I can integrate that down And what we can do is we can break this down into, this was a 70-second interval, we break it into 10 7-second intervals and plot the energy transfer associated with this. And in fact, what we find is we find that bipolar signature is persistent over this whole 70-second interval. And if we integrate that over time, we get a single reduced parallel field particle correlation plot. And we see two very clear bipolar signatures of energization that are associated with the Landau damping of kinetic alphane waves that are either propagating up the magnetic field or down the magnetic field. So this was the first like definitive sort of spacecraft observations of Landau damping in a space or astrophysical plasma. Later, a graduate student of mine extended this work and looked at 20 different intervals using the same technique. And we found these bipolar signatures either both sides like we see here or on one side like we see there in 19 of the 20 intervals. So it tells you that this electron Landau damping is actually happening pretty ubiquitously out there in the magnetosheath. And for those one-sided signatures, we said, well, what's going on there? Well, it turns out if you take the pointing flux, that gives you the wave energy flux, the electromagnetic energy flux in one direction or the other. If it was balanced turbulence with equal fluxes in both directions, this value should be 0, but it's not, it's off, which means that all the waves are moving in the forward direction, which is why we only see the signature there. So even these asymmetric signatures are still signatures of Landau damping of kinetic alphane waves. And then to really, and this is the really important result, is we can say, look, for each of those 20 intervals, we can estimate from the fluctuations in the inertial range using a cascade model, what is the cascade rate of energy? And I can plot that predicted cascade rate of energy against the actual directly measured electron energization rate using this technique. And you know, because these cascade rates are really only order of magnitude estimates, that's this solid line, what we want to do is go up or down by about a factor of 3. So really anything that falls within these dotted line, that band bounded by the dotted lines, is really consistent with like the entire turbulent cascade energy cascade rate. And so what we find here, again, I said that 19 of these 20 intervals showed evidence of Landau damping, but about a third of those intervals had electron Landau damping rates that were comparable to the total turbulent cascade rate. So it tells you that this electron Landau damping is actually a significant dissipation mechanism for the turbulence. Now, the question you may ask is, what the heck is going on down here? Okay, because some of these intervals, I mean, they're only, maybe a few percent or 10% of the total cascade rate. Where's the rest of the energization going? So we can focus on this one interval here, and we looked at it a little bit more closely. So here again, the measurements and our burst mode where we have the highest cadence measurements are between these two dashed lines. And what we find if we take a plot of the polarization of the magnetic field of the fluctuations, we see left-hand circularly polarized waves in this region. Those are ion cyclotron waves. And so we said, well, let's take this interval and compute it with the perpendicular field particle correlation. And so we did that. This was a prediction from some earlier numerical simulations of what that cyclotron damping signature would look like. When we did that with the spacecraft measurements, we got something that looked very similar. We got a lot of energization between 1 and about 3 thermal velocities and a little bit of loss below that. And at this point, my student had become a postdoc and he was not completely convinced himself. So he said, well, let's look at this. Velocity space is 3-dimensional, and I've done this, gyrotropic picture here where I've averaged over the gyro phase. What if instead, because there's no structure in this direction, what if I integrate over V parallel and look at the V perp 1, V perp 2 directions in that plane? So he did that, and we had never seen this before, never even thought about it, and it generated these little bipolar signatures. We say, well, is that cyclotron damping? Does it look like what you expect? So what we did was we took a linear Vlasov-Maxwell dispersion relation solver and solved for what you would expect to see in this case for a damped ion cyclotron wave that's undergoing ion cyclotron damping. And this is the pattern that you see. This is exactly what theory predicts you should get. So, there are, of course, quantitative differences, partly because this is a single wave and this is a lot of turbulence going on. But you see exactly the same bipolar signatures where there's in opposite quadrants, there's either energization or loss of energy. And and the sort of the skew in these and all of that all has to do with the phase and amplitude relationships between the electric field and the ion velocity. But we understand this is pretty well. So this is the first pretty definitive identification of ion cyclotron damping directly measured in the magnetosheath. And so if we look back at this picture, you know, the electron energization was there. If we compute the rate of ion energization, it's there. So the total energization is there. So here we've shown that we can both identify different channels of energization and quantify the partitioning of that turbulent energy among species, which is, again, exactly what our turbulent cascade model or predictive turbulent heating model needs us to be able to do. So this gives us the data to be able to develop models. And of course, we've extended this now with, I've got a postdoc who's done 160 intervals where we do this field particle correlation, again, looking for electron Landau damping. And if we can determine the dissipation rates by different mechanisms, we can start to sort this by the plasma and turbulence parameters for those intervals and see if there are some obvious trends of what's going on. So one final thing, and then I'll be done, is a little bit about machine learning. So this has actually even got a few more examples, but all of these are gyrotropic velocity space signatures of energization mechanisms, okay? And they all look fairly distinct. I mean, you could distinguish those. And so, you know, machine learning algorithms, in particular convolutional neural nets, or CNNs, are really good at automatic recognition of patterns. So what we want to do is develop machine learning tools that can automatically identify these dissipation mechanisms. So you can analyze thousands upon thousands of spacecraft observations, feed it through the mechanism. It can tell you what is the mechanism, quantify that rate, and then you can sort that by the various turbulence and plasma parameters so that you can develop new turbulent models. So in conclusion, we want to understand the turbulent heating because it's really critical for interpretation of astronomical observations. Here's the Event Horizon Telescope image of Sagittarius A star from last year. We want to predict the partitioning of energy, both between protons and electrons and between parallel and perpendicular components. And we want to do that as a function of plasma and turbulence parameters. This goal requires that we both identify the physical mechanisms of the turbulent dissipation and quantify the rate of energization by each mechanism. And so we have a proposed strategy to develop improved predictive models of turbulent heating. So we use this field particle correlation technique, which can identify the mechanisms based on their velocity space signatures, and it can quantify the rate of particle energization by each of those mechanisms. We can use kinetic simulations to determine all of these velocity space signatures because we can control the situations there, and then analyze a very large sample of in situ spacecraft observations and use machine learning tools to identify automatically the dominant mechanisms. And then we can determine the dependence of those mechanisms on the plasma and turbulence parameters over at least the range of what we can observe. And then we can use those and combine, synthesize all that information to construct new predictive turbulence heating models. And those can then be used with global simulations to predict the macro scale evolution of the system, such as this prediction of the evolution of a black hole accretion disk. Thank you.
Questions for Greg? But of course, makes this, I think, fantastic is that this has been something that has been speculated and debated in space plasmas for, you know, decades, that whether it's Landau damping or something. So it's, I think, fascinating to see that we are finally seeing some kind of a real proof of this in situ with the spacecraft. So it is quite amazing to finally be able to say that, oh, it's a Landau damping or.
Thank you.
So I think I'll use one of my, since I already have the mic. So one of the questions I had is that, are you worried about the intermittency of turbulence? Maybe not in the case of solar wind where the inertial range is short, but what about, for example, in the systems of like black hole accretion flow where you have astronomical Reynolds numbers of 10 to the 20, or which gives you lots of inertial range for building up intermittency?
Yeah, you know, I mean, intermittency, of course, happens. And I mean, you know, if you actually look at numerical simulations, because you can just look at J.E, which is the rate of work done by the electric field as a function of space. And you see that it's not at all uniform. I mean, it's very localized in various places. And so, you know, this field particle correlation technique is a local mechanism. You go to a single point and you have some time series of measurements and you average over that and you get some signature. And of course, if you have some arbitrary simulation domain and choose 100 points in it, you know, maybe 70, 80 of the points, you don't see anything. There's nothing interesting. But in the points where you do, you're going to get a signature, and then you need to be able to look at what that velocity space signature is and try to identify the mechanism. So it really is a bit agnostic to the idea of intermittency. It's just, obviously, I cannot measure dissipation if there is no dissipation going on where I make the measurement, right? So there's of course a little bit of luck in that if you're trying to analyze a particular simulation. But you know, if we're doing simulations, you know, we can look at lots of different points and do this analysis and find the places where the energization is going. Of course, if you just look at J.E, you know where that is peaking, so you can go to those positions and look. And with spacecraft observations, of course, we don't have any control. But again, all we can do is estimate what is the dissipation at the place where you were measuring. That's all we can really do. So I don't think it actually matters too much. And you know, I mean, if you wanted to answer a question like how intermittent is it, then you sort of would have to say, well, I'm going to take an arbitrary sample of many observations that hopefully has no selection bias in it, because spacecraft observations do have selection bias, and just say, okay, well, how many are seeing nothing and how many are seeing something? Then you can get statistics of the intermittency of it. But if you just want to identify the mechanism, know what the rate is, I think that is a less significant concern.
There's a question also, but let's go Ethan first and then Vlad.
Thanks for the great talk, Greg. I had a question about your alpha, like lambda damping alpha waves diagram.
Yeah.
The two peaks. They were quite broad. So what defines the breadth of the peak? Because like lambda damping is derivative.
Yeah. Let's find the simplest picture of that. So yeah, so this one here, yeah, actually that's a very good question, and actually my recently graduated graduate students spent a lot of time looking at electron Landau damping and trying to understand this. And in fact, there are two things that can make that peak very broad, because it can be narrow. One of them is it's related to how strong the damping rate is. If it's a very strong damping rate, you tend to get broader peaks, and we've shown that correlation in a paper that was, well, it's almost going to be published. It's just in the last round of review. But the second thing is that if the magnetic field moves around in direction, because this quantity is normalized by V parallel. That's the velocity parallel of the magnetic field. So if the magnetic field kind of moves around a little bit, as it does in a turbulent plasma, it can kind of smear out those signatures a little bit and give you a little bit of broadening of those signatures. But what we have shown, and we've done this with like single kinetic Alfvén wave simulations, is that as you go from larger scale kinetic Alfvén waves to smaller scale kinetic Alfvén waves, the damping rate increases and the width of those signatures increase. So we've been able to quantitatively sort of understand how it looks like that.
Vladimir also has a question.
Yeah, nice talk as always. So at a few points in your talk, you mentioned the signatures being unique, and I was wondering how strong of a statement is this? Can you imagine any situations where maybe different mechanisms could lead to signatures which maybe look very similar?
Yeah, I mean, this is, you know, I mean, to prove that they're unique, you have to determine all of them, right? And I obviously cannot do that. There's certainly a big dose of optimism in that statement, I will admit. But if you go to, let's see here, here I've got the picture of the most mechanisms here. All of these, these are the same mechanism and they look more or less similar. But the one thing that can be a little bit complicated is, and this one is reconnection, is reconnection, a strong guide field looks a little bit like electron landau damping, and it's a bit hard to tell the difference sometimes. But again, then it comes down to quantitative things. Like these structures have to be related to the phase velocity of that wave. And there's going to be a range. And so in fact, the phase velocity, range of phase velocities for the particular parameters, this is a beta of 0.1 simulation, are between these two peaks. So that zero crossing between the blue and the red happens to fall between them. So, that tells you that, look, this is probably a electron landau damping wave. If you have reconnection, sometimes the signatures are in different places that aren't associated with phase velocities. So I think there probably can be certain instances where things happen to line up in the same place. But if you vary it as a function of parameters, you can usually tell the difference, because as you change beta, that phase velocity is going to move around a little bit. And if the signatures don't move with that, then you're pretty sure that that's probably not what it is, right? So yeah, it's a little bit of an optimistic statement, but I think that by and large, I mean, we've done a lot of these things now, and you can kind of distinguish most of these from each other, I think.